So this is the 8th lecture, online lecture for ECE 341 random processes. Today we're going to continue our discussion of multivariate random variables, vectors of random variables, and we're going to look at a few pretty simple ideas, the idea of independence, functions of random vectors, and then we're going to look at some concepts involving expectation, which includes the ideas of correlation and covariance when applied to vectors. This leads to ideas like what are called autocorrelation and cross-correlation, autocovariance and cross-covariance. Auto means with self, cross means between two different things. So we'll see that as we move along. Most of these concepts are pretty straight extensions of what we've looked at before. So I've pre-written most of the lecture and we should be able to get through it relatively quick. Independence is an extension of what we know. If we have a series of random vectors, x1 through xn, and if they are independent, then for all observations, we require that the probability mass function, that's px1 through xn of observations, little x1 through xn, this is in the case of discrete random variables, that it has to be a product of the marginals. We had seen this before for bivariate, right? That two random variables were independent if the joint distribution was a product of the marginals. For n random variables, it's the same thing. We just need a product of the n marginal distributions. In the case of discrete random variables, that's the marginal probability mass functions. If we look at the continuous random variable case, it's the same idea. The joint CDF of n variables now is just a product of the n marginals. Independence turns out to be pretty simple. We can take a look at this idea in a slightly different way and just say that the PMF or the PDF are separable, right? They are separable into a product of marginals. If we continue the quiz that we had last time, so we were working with quiz 8.1, and we had derived or figured out what was the probability of this derived random vector y, and we went through some math on that, and we found out that the probability mass function of that derived random vector y was 1 minus p, that quantity cubed, over p cubed times p raised to the y1 plus y2 plus y3. Well, this one's not too bad either because of the properties of exponentials. We can certainly write this out as a 1 minus p by p times p to the y1, and then we can multiply that times 1 minus p by p times p to the y2, and we can multiply that by 1 minus p by p times p to the y3. And because of the work we had done last time, we recognize that this here is just the marginal distribution py1, right? So that's py1. The next one is just the marginal distribution py2. And the last one is the marginal distribution py3. Because the joint distribution is just a product of the marginals, we could just sit there and say, therefore, right, the guy y, right, are independent. They are independent random variables. It's a vector of independent random variables. There is a key, very special case, very important to us for this case of random vectors where maybe the number gets quite large. And this is something called independent and identically distributed. We've already handled the independent part. What we need to think about is what this additional terminology of identically distributed means. Really, what it says is that each of the marginals, not only is it a product of these marginals, but each marginal has exactly the same form. This is something that shows up quite a lot, and so what we will find in this case is that independent identically distributed, it's kind of a long one to write out, is almost always just abbreviated as IID. So we're going to talk about IID random variables, independent identically distributed random variables. The idea is about the same as what we saw before. We have a joint distribution, right? This is a joint PMF. Below it is a joint PDF, something along those lines. And we're still showing them as being a product of marginals. That's the independence part, right? The identically distributed is that each one of these P's, right? Each one of these P's has a distribution in terms of a variable x, and you'll notice there's no subscript on that, right? So this is px of the observation x1, px of the observation x2, or fx of the observation x1, or fx of the observation x2. What does that tell me? It tells me that each one of these p's, right, is exactly the same. That's the identical part, identically distributed. And what it does is it gives us a very regular structure, right, of that product of marginals. And we'll find out that this really helps us out. This is something that greatly simplifies much of our work with stuff. A very simple example that we could look on this. I'm just going to show a little bit of MATLAB code. You probably have already done this before. So if, for example, I did the rand function, what do we know the rand function generally does? If I just passed it a single number 1, like if I did rand of 1, that would create a single observation of a uniform random variable, right? A uniform random variable on the interval 0 to 1. If I did something like a rand 1000, comma 1, that is going to generate what? It's going to generate a random vector, right? A random vector of 1000, right? IID uniform 0, 1 random variables. So they're independent, okay? MATLAB doesn't default anything with any type of dependence on it, and it assigns them all the exact same distribution. They're all going to be uniform 0, 1s. So this is a case MATLAB's really good at generating things like IID random variables. There's a slightly related function that is the rand n, right? So that's a random number generator that goes according to a Gaussian distribution. And if I passed it 1000, comma 1, that would give me again a random vector of 1000 IID, but in this case normal, right? It's a standard normal 0, 1, so 0 mean and unit variance random variables. So programs like MATLAB and other programs, oftentimes when they generate big lists or big vectors of random numbers, they oftentimes follow this model of IID, certainly a simpler case. We'll switch gears here and quickly go through the basics of functions of random vectors. Again, this is just a logical extension of what we've seen before. We don't have to spend a huge amount of time on it. It can be more complicated just because the number of sums or the number of integrals increases, and maybe visualizing the relationship that creates a particular region might be a little more difficult. But as far as the underlying concept of this, they are done exactly as we had done before. So in this particular case, I'm going to think about generating a new random variable, w, that is a function of a random vector x, okay? For the time being, we'll just look at w as being a single thing, although it is completely plausible to think about having a random vector come out of a function of a random vector. But let's just leave it as a single random variable that comes out. That single random variable, being a function of random variables, will have its own distribution. If it was discrete, it would be a probability mass function. If it was continuous, we would get to the probability density function through the CDF. Let's take the discrete case first. So the probability mass function is the probability that W takes on a particular observation, little w. How do we do that? Well, we just add up. So we're going to add up all x such that that mapping function g of x gives us that desired value little w, and we add up their corresponding probabilities. Because of each of these probability points of the probability mass function being separate point, they are mutually exclusive, and we can just add their probabilities to get it. Discrete cases is simple to visualize, coming up, especially in super higher dimension or really high dimension cases, coming up with an automated way to count up all those points where x, all the points x such that g of x equals w, can be a little bit of a head scratcher. If we look at the continuous random variable case, we are going to start with the CDF. So this is the CDF method, and the CDF says what? It's the probability that a random variable cap w is less than or equal to some observation little w. And so what is our game plan here? We just convert that into those values of x that share, right, those same values of w or less, a little w or less. So we're looking for all the mappings g of x such that they are less than or equal to little w that create some n-dimensional shape, and we're going to integrate over that. Again, that kind of operation might be simple or it might be a little bit complex, but the idea is simple in itself. We look at all those mapping values that are less than or equal to little w, and then we just integrate up the corresponding probability density. I have shown this, right, so that it goes dx1 all the way through dxn, so there's an implied order of integration here, starting with variable x1 going outward towards xn. We know, though, that this order of integration really is arbitrary, so we can swap that around to whatever provides the most simple structure for us so we can get to an answer. Let's take a very quick look at some of these ideas of doing a derived random variable, but in the case of independent and identically distributed, I'm going to do the derivation for the maximum operator. So I'm going to let y be equal to the max of a list of random vectors x1 through xn. So you could think of having n random variables x1 through xn, and I want to find out which one has the largest value, and I'm going to assign that to my random variable y. Because it is a derived random variable, right? Y has its own distribution, and we certainly could be interested in that distribution. So how would I find it? Because I'm going to be looking in this particular case at the continuous. I said it was continuous random variables and they're independent. Because it's continuous, I'm going to use the Cdf method. And so I'm going to look at fy of y, cap fy of y. We know that's the probability that y is less than or equal to little y. Well, what is that in terms of our value x? We know that that is the probability, right? That x1 is less than or equal to y, and that x2 is less than or equal to y, all the way up to xn is being less than or equal to y. If y is the max, right, all of our other x variables have to be that value or smaller. So probability that y is less than or equal to little y is the same as probability that cap x1 is less than or equal to little y, all the way up through cap xn as being less than or equal to little y as well. Okay, so what is that equal to? That is in itself equal to, because it's IID, that is the CDF of just a single one of those random variables, fx, at y, and because there's n of them and they can all be separated out, we just raise it to the n power. So we're basically going to be knowing that this joint probability up here is going to be a product of the CDFs of each individual one. You could talk about these as being the marginal CDFs if you like. And because of the independence, we just get to multiply them all through. Okay, so how do we get then the fy of y? We just need to differentiate our CDF fy, right? So we're going to take the derivative with respect to y of my fy of y, and we know that that's based on the CDF of x using observation little y. So if I take the derivative of something raised to the n, I'm going to get n times that something, so this is going to be fx of y, right, raised to the n minus 1. Just go one less. This is basic calculus. And then I differentiate that thing inside the brackets, right? And the derivative of a CDF is just the probability density. So little fx of y. And we're done. We have the distribution for the max of a set of continuous random variables that follow this idea of being independent and identically distributed. Turns out to be a really simple operation. It doesn't matter what n is. You could have 10 million of these random variables x1 through x 10 million, right? And if we were letting y be the maximum value of all 10 million observations, its distribution could be easily gotten by taking n times the marginal CDF, if you will, of x, evaluated at the value, the max value, little y, raised to the n minus 1 times the probability density of x of y. We can do a similar kind of calculation. I'll leave this up to you, or you can check it out in the book as well. If we have w being equal to the minimum value of all those guys, x1 through xn, we can do a CDF type of operation. So the CDF of w can be put in terms of the CDF of just a single one of those random variables x. We are still looking here at the case of IIDx, right? So we aren't changing that. And then we can differentiate that, and that gives us the probability density function, probably the thing we like to work with most often in the case of continuous random variables. And it's going to be an n times the difference 1 minus the CDF raised to the n minus 1, and differentiate the middle there, and you get the probability density fx of w. This second step, right, going here is just one you don't even have to really do much work on. You can see it just as we go. Okay. So let's talk expectation of a function of a random vector. We're again going to just be primarily thinking about this idea that this function of a random vector gives us a single random variable out, like that min case or that max case that we just treated. If I want to look at the expectation of that function of a random vector, expectation is just taking whatever it is you're expecting, right, times its particular probability. Just as in the case before when we looked at derived random variables, you don't need the distribution of the derived random variable. I don't need, so for example, if I let y equal g of x, right? I certainly could find my cap py or little fy, depending on whether it's discrete or continuous. I could certainly do that and use that then to find the expected value of y, which is the same as the expected value of gx. But if I don't need the distribution, if I'm just interested in the expectation, why go through all that effort to find the derived random variables distribution? I can go straight to using the known distribution of our random vector x. So in the case of expected value of some function of a random vector x, we just take what we're expecting, that's the g of x, we weight it in this case because it's a function of the random vector x, we weight it by, we're doing this for the discrete case, the probability mass, the joint probability mass function, and then we add up all the points that are part of our corresponding range spaces on each of the elements of that random vector. So x1 an element of sx1 all the way to xn an element of sxn. We're just adding over these regions of support for each of the elements in our random vector. If it happened to be a continuous random vector, well, we'd still do the same thing. We would take what we were expecting, g of x, right? We'd weight it by the probability density function in this case, and now it's just a straight integration. That straight integration can be taken from minus infinity to infinity in all cases. In the areas where it's not part of the region of support, the probability density function, right, will just be 0, and those guys will automatically fall out. And then we integrate according to some order. I've drawn this as dx1 through dxn, but we do know that that is swappable. You can make whatever order is simplest for you. If our x are independent, and the thing that we are taking the expected value of is separable into a product of a bunch of functions, each of only one of those random variables, x1 through xn, then we get something nice. The expected value of that function of the random variable is the expected value of the product. That's the product of all this sort of stuff. And if you plug that all in, because of the separability of what we are expecting, because we can write g of x as g1 through gn all multiplied together, and because of the independence of x, its joint distribution can be written as a product of all the marginals, right? So px1 through pxn for discrete, or little f x1 through little f xn in the case of continuous. And then we can collect each term that is associated with x1 and all the ones that are with x2, and what we end up getting is just a product of one-dimensional expected value. So expected value of g1 x1, expected value g2 x2, and this really can be a lot more simple, right? Why? Because this guy is going to involve just a single sum or integral. It's not going to be an n-dimensional one, right? It's just going to be a single one, and so that's easier to visualize. It's easier to mechanically carry out. Just makes everything easier. Independence is absolutely your friend. It absolutely will simplify things, and it makes them particularly simple in these other cases, like if you're taking expected value of some function of those random vectors, and that function is itself separable. So let's look at a couple useful functions of random variables, a couple special cases. These are derived out in the book, so if you want a little more detailed work on this, I certainly encourage you to look at the book, but we'll just go through these pretty quickly. In this particular case, we're going to think about having some known random variables, x, and that we are going to create a new random variable, or random variables y, through a linear transformation of these values x. So we're going to let, in this first case, we're going to assume we have a random vector x going 1 through n, and we are going to create a random vector y also going 1 through n, where each element y, right, is just a simple linear transform of its corresponding value x. So yk is equal to xk scaled by some value a constant that is going to be left here as positive. You could also handle the negative case, it's not hard, plus some offset b. If we have that, the joint CDF of that linear transformation on x, that joint CDF of the new random vector y, can be gotten from the CDF of x, right? And we're just going to be taking y1 minus b over a all the way through yn minus b over a. How might we get part of this? Just take a look at this expression that we had for y, right? And let's solve it instead for x. Subtract b from each side, and I'm going to get yk minus b. being equal to AX, right? So I would have equal to AX, but then I'm going to divide by A, so divide by A, and that gives me my X, something like that. And what do I see? I see that that expression YK equals AXK plus B is equivalent to XK being equal YK minus B over A. So getting my Fy of Y, right? I can just take what those values of Y translate into. A YK goes to an xk being expressed as yk minus b by a. That's all of this stuff. So we're just getting it in terms of the known. This is basic CDF method stuff. And in this next step, then what do we do? Continuous. These are continuous random variables that we're talking about, and so we're going to differentiate it to get the probability density function for that derived random variable y. That is just a linear transformation of the x's, where it's just 1 to 1, one value of y going to one value of x. And we know that the derivative of this joint CDF fx is just going to give me the probability density function, little f sub x, and we have all the arguments in there. And each time we differentiate, we have to differentiate those arguments as well, right? So when I differentiate this argument, for example, with respect to y1, I'm going to get 1 over a, right? When I keep doing that all the way out to the last one, y of n minus b over a, and I differentiate that one with respect to yn, it's also going to give me a term 1 by a. How many different terms 1 by a are there? There's n of them, and so I'm going to get a product of all of those guys, which is why I have that term 1 by a to the n out front. We can pretty easily see this case where you have xk going to yk, just 1 to 1 type of thing. We can generalize this result, and this one turns out to just be more powerful. It's a generalization of the linear transformation, so I'm going to create still my random vector y, and we're going to get it from x, but now instead of multiplying just one value of x to give me one value of y, we're going to modify the whole vector x by a matrix A. This means that y1 might be a function. It's a linear function of all the different values x1 through xn, or any subset of those. And then we'll do a vector offset b. So it's just a generalization of that linear transformation. We are going to require that A is an invertible matrix. Okay, so we will look at that as being a linear transformation using this invertible matrix. Well, what do we get? You can check out the proof in the book. The probability density function of y in this case is derived directly from the probability density function of that random vector x. What did we have in the 1-to-1 case? We had something like a what? It was a y minus b by a. What do we get down here? We still have the y minus b, just vector style, right? The divide by a is accomplished by this a matrix now inversed. This is all vector operations. You wouldn't divide by a matrix, so the appropriate operation here is going to be a matrix inverse. And this 1 by a out front that came out of the differentiation of the CDF that we had, right, ends up giving us a term that's related, and this is just going to be 1 over the determinant of a in absolute value. The absolute value there is a necessary piece to handle all different possible a's that you can think of. In fact, if we went back to this other one where we were deriving this result, fy of y being 1 over a to the n, if you wanted to work on the case for a less than 0, you could get this very simply by just letting us have something like magnitude of a in there. I'll let you take a look at that on your own. So in this particular case, we can easily get a transformation, a linear transformation. We can get the distribution of the resulting random vector, right, through a pretty simple operation on the known distribution of the originating random vector x. It just involves some linear algebra. I'd mentioned in the previous lectures that we're going to be making a return to linear algebra. Certainly going to be the case today, and as we go forward, linear algebra is going to allow us to kind of manage these larger number of random variables that we're going to be dealing with. Okay, so let's switch gears just again. So we know that we have a vector of random variables, right? That could be x or y. We know that they have a particular distribution, right? And like any kind of random variable, we oftentimes are just interested in some summary statistics about those random variables. Those summary statistics tell us things like what do we expect each particular value being, how much variability there is there some interaction between those? So those are the cross kind of terms in there. And so we're interested in this certainly for random vectors, just like we were for the case of single random variables or bivariate random variables. We're just going to do the logical extension to higher dimension. So we're going to be looking at vector expectation, and we're going to be looking at things like what are called correlation matrices. So let's see what we can do with that. Expected value of a vector, I think, is the easiest one. So let's look at expected value of the vector x. We're just going to call that mu of x. That's also a vector quantity, right? And if you think about what x is just a column vector. Expected value of a column vector is the expected value of each element of that column vector. So expected x1 all the way down to expected xn, and then I just stand it on edge to make it a column vector. This is part of that just writing efficiency. This is called a first order statistic. It's first order because you only see single values of a random variable. There's an expected x1 or an expected x5 or an expected xn. There's only one of those variables by itself being having that expectation operator working on it. So first order statistic. We've seen that univariate, and we've seen that bivariate case, and now it's just an n variable case. So we get n dimensional column vector coming out. Expectation of a vector x gives us just a vector of expectations. So the individual means, you could get this from the marginal distributions from x1 through xn, right? Because things like this expected x1, right? That's just a function of that single random variable x1. And so you would only, that e out there, the expected value out front, would just mean a single sum or integral with respect to x1, and you'd only need the probability density or probability mass function for x1. Second order statistics involve a product of terms. So we've seen stuff like this in the univariate case, for example. We saw things like variance, right? That was a mean adjusted second moment. So it's a second order statistic, something squared, if you will. And in that particular case, looking at the variance, it was of a variable times itself, right? We can also take things like an expected value of one variable times another variable, or the mean adjusted versions of those. That could lead to things like covariance, okay? It's still second order because it still involves the expectation of what is effectively a power of 2. Sometimes it involves the variable with itself. Sometimes it involves the variable with something else. So we're going to look at all the different cases that we can deal with, and we'll start this by looking, or initially saying that we have some vectors of random variables, and we're going to let there be a vector x, and there's a vector y. Okay, both column vectors. If I'm interested in all the second order statistics on this, I'm interested in all the something times something pairs or combinations that can come out of that vector x and that vector y. Well, an outer product does that exactly. An outer product gives all possible product terms, and we can get an outer product by taking a column vector and multiplying it by a row vector, something along those lines. It's a very quick example. Suppose that x was x1 and x2, so I could have something like that, x1, x2, right? And then I could have y be something similar. It could be a y1 and y2, right? I'm going to leave the first one, x, as a column vector. I'm going to make y a row vector by that little transpose operation, and I'm interested in this product. Well, you should remember from linear algebra doing stuff like that. This first one is what? It's 2 rows by 1 column. The second one is one row by 2 columns. It is conformable. Those inner dimensions match, and then the result should be a 2 by 2. Okay, it doesn't have to be just limited to 2. If n of x was an n-dimensional guy and y was an m-dimensional thing, the outer product of those two is going to give me an n by m result, right? N times m different cross terms that were there. If I continue this example over here, what do I get? I would get something like an x1, y1. I'd get an x1, y2. I would get an x2, y1, and I would get an x2, y2. Those are all the possible cross products we can think of between x and y as an example. So we will be looking at these second order statistics using cross products, basically. It could be a cross product between x and y. It could also be a cross product between x and itself. That would give me things like x squared, right, or x1, x2 kind of an idea. The correlation between a vector with itself. Just as we can have the expected value of a vector, right? We've already seen what that looked like back when we did the mean vector, right? We can also have the expectation of a matrix, and it's really not anything that would be difficult. Expected value of a matrix is a matrix of expectations because expectation is a linear operator. So let's go ahead and get started on this. Let's look at a variety of these second order statistics. The first one we'll look at is an idea of vector correlation. I'm gonna call this more often probably autocorrelation. I think that's a better term in some ways. Auto as a term means self, so this is self correlation. And so we are going to be looking at the expected value of the outer product of x with itself. This is looking at all the pairs of terms, right, between a random vector x with itself. So x1 through xn, outer product with x1 through xn. That gives you terms like x1 squared, right, or xn squared. It also gives you all the cross terms like x1, x5, x1, xn, x2, x3, all of those guys in there. Because x is an n-dimensional vector, the outer product here, x of this expectation of x transpose is going to be an n by n. It will be a square matrix. And we're going to go ahead and assign that a cap r sub the vector x. So this is autocorrelation, correlation of a vector with itself. It is pretty easy to do, right? It's just the expectation of that outer product, all the possible cross terms. Do a very simple example in here. Let's go ahead and set up x as being just a pair of random variables, x1 and x2. Make that a column vector because that's the standard notation for when we deal with vector random variables, stand them up on end. Then we can look at what? We can look at the autocorrelation of x, that is the expected value of xx transpose, and we already saw an example of how we could take a two-element vector times the two-element vector transpose, that's just the outer product, and I'm going to get things like x1 squared and x2 squared, and then all the cross products x1, x2, and x2, x1. Something like that. I'm taking the expectation of that matrix. That's going to be just the matrix of expectation. So I get a matrix, right, of all the expected values of each of those terms in the matrix. So I'm going to get expected x1, expected x2, each squared, or the cross the cross terms, expected x1, x2, or expected x2, x1. If I take a look at that then and just recognize those off-diagonal elements are these correlations that we had seen before when we talked about bivariate, right? Pairs of random variables. And this is always the case. So when we look at this autocorrelation matrix, right, this autocorrelation matrix, we're going to get a diagonal of expected whichever variable it is squared all the way out to however many we have, n of them. And then all the off diagonals are going to be these correlation functions between all the cross terms, x1, x2, x1, x3, and so forth. Correlation is fine, but probably the more common and useful one, just like we saw with the bivariate case, is to talk about a mean adjusted version of correlation, that is covariance. And if I do it as the covariance of a vector with itself, we could call that vector covariance. I prefer to call it autocovariance, so covariance with self, something like that. It's just going to be our vector, right? Mean adjusted, so subtract off its mean, take the outer product of that guy with itself. So again, you take the vector minus its mean and just transpose it, multiply those together in the linear algebra kind of vector way, and then we take the expected value. That is our covariance, autocovariance matrix. If we go through a little bit of math on that, I'm not gonna do it here. You can check it out in the book. That is just what? It's our correlation, autocorrelation function minus the outer product of the means. Think about what we had for covariance when we were just dealing with pairs of random variables. It was the correlation minus the means squared, right? So we got that mean squared kind of term in there. So it's structurally very similar. It's just going to be made into a vector style, something along those lines. If I expand that out, I think you'll see something that is sort of expected based on what we saw for the autocorrelation matrix. So this autocovariance matrix has what? It has a diagonal of all the variances for the elements of my random vector x, right? So I get the variance of x1, variance of x2, all the way down to the variance of xn. So the variances go along the main diagonal. And then the covariances between elements within our vector, like this first one is covariance x1, x2, and across this first row, it's going to go all the way out to the covariance between x1 and xn. All of these covariance terms are the off-diagonal elements. And if you look in a kind of a symmetrical way, right, there is some symmetry going on here. So in the upper right, this guy here, we're going to have covariance x1, x2. And if you just look at kind of that mirrored version around the diagonal, you're just going to interchange the order of the elements that you're doing the covariance on. So that's covariance of x2, x1, something along those lines. Something we might note is that if we have x1 through xn that are independent, right? Independent random variables have a covariance equal to 0, and that means all of these covariance terms here and all the covariance terms here would all go to 0, and we would end up with a diagonal covariance matrix. So if you have a diagonal covariance matrix, what it's going to give you is it's going to give you the variance of each element in your vector, right? And everything off diagonal will be 0 because they're independent, and we know independent random variables have covariance equaling to 0. This is a really nice case because diagonal matrices are super easy to compute and work with. They have super easy inverses. All that kind of stuff just becomes much, much simpler in the case of not having that kind of cross relation where we have our covariance equaling to 0. We can extend these ideas, and this is a little different than what we've seen up to this point. We can extend these ideas to an idea of correlation or variance, covariance again, but we're going to do it not with something in itself, not between x and itself. We're going to do it between x and another random vector y. So these are not autocorrelation or autocovariance, they are cross correlation or cross covariance. That just means that our correlation idea or our covariance idea is not going to be taken of something with itself, it's going to be taken of something with something else. These are still second order statistics, right? They're still second order statistics because they involve expectation of some squared random variable or random variable combination. So this first one, cross correlation, we're going to still use R because it's a correlation, but it's not going to be subscripted just X, it's going to be subscripted XY, right? Because it's going to be the cross correlation between vector X with vector Y. And it's what you would sort of expect. It is the expected value of, something squared terms. So we're going to get X, and it's not X with itself, it's going to be Y. So we're going to do the outer product between X and Y. I should make a comment here that remember X is a column vector. So we might have something like n rows by one column, right? And y is also a column vector. It might have a different number. It could have the same, but it could have something different. So it could be an m by 1. When we transpose that, it is a 1 by m, right? The ones here being equal, that's why outer products kind of work. It tells us that we're always going to be able to take the outer product between vectors. Doesn't really matter. Doesn't really matter whether they're not the same size or not. And what comes out of this whole thing is going to be an n by m matrix. So in the case of cross correlation or even cross covariance, we are going to have the at least possibility of having a non-square matrix come out. It could be square if there were the same number of elements in y as there were with x. If m was equal to n, then you'd get a square matrix coming out. But it is possible to get a non-square matrix. For autocorrelation or autocovariance, you would always get a square matrix. Cross covariance, it's the same sort of an idea. It's just now we're mean adjusting. So we take x minus its mean, vector style, and we take y minus its mean, vector style, transpose it. That makes it the outer product and take the expectation. So cross covariance. All right. So what have we done at this point? We've just been extending our ideas of random vectors. We started out by talking about independence among elements in random vectors. We talked a little bit about functions of random vectors. We looked at the idea of expectation of random vectors, started out with the first order statistics, and now we have been building into second order statistics. We looked in those second order statistics as second order statistics involving something with itself, so things like auto correlation and auto covariance. And then we looked at second order statistics between a random vector x and a random vector y. Those are the cross versions, so things like cross correlation and cross covariance. Let's combine all of these things with our friend, the basic linear transform. This just happens a whole ton in a whole bunch of engineering applications. And so this idea of cross-correlation and cross-covariance, especially when a vector y is coupled to a vector x through a linear transformation, just turn out to be really, really useful. So let's start it this way. We're going to go ahead and start with some random vector x. You could call that a vector of random variables of interest. They're going to have some corresponding statistics, like there's going to be a mean vector, right? There's going to be an autocorrelation matrix, that's square, and we're going to have an autocovariance matrix as well, C sub x. Then we're going to go ahead and take those random vector x random variables, right? And we're going to create a new vector of random variables y. In this particular case, we can think of y as being a derived random variable, but it's derived in a very particular way, and it's a nice way. It's through a linear transformation, and because we're talking things vector style, it's going to be a linear transformation as we would describe with some linear algebra. So to take x, we're going to scale it by some matrix A, and then we're going to add an offset B. So it's a lot like you would expect. It's still a straight line equation. Y equals mx plus b, if you want to call it that, right? It's just matrix style and vector style, and so we get the vector y as being the matrix A times x, right, plus b. It is not necessary, although it is common that y has the same dimensions as x. If y has the same dimensions as x, then A would be a square matrix, right? And B would be the same dimension as x and y. If y was a different dimension than x, you could find then that B would still have the dimensions of y, right? It wouldn't have the dimensions of x in that case, and A would no longer be a square matrix. It would be a matrix that converts the dimensions of x, call it n, to the dimensions of y, m. So it would be something along those lines as far as dimensions m by n. If we have this linear transformation, and we're not going to go hugely through the proofs on this, I might show a little bit about how you get the first one. The rest of them are just kind of some tedious linear algebra. There's proofs on this in the book and in the internet if you want. We're going to mostly just use the results. If we did a linear transformation of y, right, from x using this matrix A and B, then we can tell something about the kind of basic summary statistics of that random vector y. For example, the mean of random vector y is just going to be related to the mean of random vector x transformed by that same matrix A and offset by B. How do we get that? Pretty easy. We're looking for what is mu y? It's just the expected value of y. But what is y? We knew y, right, was ax plus b. So we're looking for the expected value of ax plus b. Expectation as being a linear operator, right, would tell me that I would get the expected value of a sum is the sum of the expectations. So I could have the expected value of ax, right, plus expected b, if we wanted to be complete in our details. That first one, a is just a set of constants, so it can be pulled outside of the expectation. So that would be a expected x, right? And then the expected value of a constant is just that constant, so we get b. And what was expected x? That's just mu x, and so we get the result coming out. All of these results that I'm getting have similar kind of flows. They just get a little bit more tedious because we're usually involving maybe more cross terms, more matrix kind of pieces in there. There's more factoring out that we have to do. So what else can we say about y? We can also say something about y's correlation matrix, so R of y. We can get that from the correlation matrix of x. That's not a surprise. And the necessary pieces in here is that we're going to pre-multiply R with A and post-multiply it with A prime. A reminder, if you're still sitting there and it's been a while since you've done some linear algebra, just a reminder that things like multiplication, when you're working with vectors and matrices, multiplication is not commutative, right? Commutative means order of multiplication wouldn't matter. You get that when you multiply real numbers. If I multiply 2 times 3, it's the same thing as if I multiply 3 times 2. We can interchange the order. Not true for linear algebra. The matrix A times the matrix B is not equal to the matrix B times the matrix A, for example, or vectors, or whatever the case may be, not in general. So you don't get that commutability, and so order here matters. You can't go changing the orders here. Back to what we were looking at, we're looking at this correlation of our derived random variable y. We get it partly from the correlation of x pre and post multiplied with something to do with a, and then we're going to get an a mu x b prime or b transpose. We get a b a mu x transpose, right? And we're going to get a bb prime, something along those lines. This is just taking our y, substituting in what is y. It's this whole mess, and then we're going to take what? We're going to take that guy times its transpose. Heck, I said I wasn't going to do it, but at least let's look a little bit at what it would look like. We would be looking at something like an ax plus b, right? That's y, right? And then we want to do something like y transpose. That's what correlation is all about. It's expected y times y transpose. So we're going to be multiplying this by the transpose. What is the transpose of ax? Well, when you transpose it, you reverse the order, right, of your guys, something like this. And so we're going to get something like an x transpose a transpose plus then a b, whoops, that didn't turn out so clear, plus a b transpose, something like that. And then you're going to multiply them all through. Take a look at the first one that we would maybe multiply. So if I looked at ax times x transpose a transpose, I would get ax x transpose a prime. But x transpose expected value is just correlation x. So I'd get a correlation x, rx, a transpose, which is exactly that first term. And you can keep doing it for all the other cross terms and you'll get the same result popping out. It's not a hard one to get, quite easy to get. Okay, we can also get the covariance of our derived random variable y, right? And that covariance is just going to come out from a times the covariance matrix of x times a transpose. You won't find any of those other kind of side terms in there, and that's because this is a mean adjusted version, and that mean adjusted just makes it simpler. So covariance is actually a bit easier than the correlation. Further, what else can we do? Now, because we have a vector y, which came out as some function of x, we can also look at things like the cross correlation and the cross covariance between x and y. This gives us some information about just how related x and y are, or in what ways they are related. So the cross correlation between x and y, again, you do this as what? This is an expected value of x, y transpose. You put in what is y in terms of x, and you go to town doing some simplification. We get the autocorrelation of x times a transpose plus the mean of x times b transpose. It's a direct substitution and simplification, just a little bit tedious. The cross covariance between x and y is the covariance of x times a transpose. So these ones are not difficult. They're relatively easy, but just a little bit tedious to go through all this stuff, and it's something you can do on your own. Okay, so to finish our lecture out, to finish everything out, let's do a quick example of looking at a random vector x and doing a linear transformation on that. We'll look at a couple cases of a linear transformation on it to create a derived random variable y. So what am I going to start out with? I'm going to start out with a random vector x, and I'm going to keep it pretty simple. I'm going to just keep two elements just so we can visualize things nicely. I'm going to show those as a row vector. We know they're a column vector, which is why I throw that little transpose up there. Just makes it neat to write, but we know that we prefer, and actually this preference of expressing things as column vectors is really crucial when we start doing some of the expressions that we had just seen of things like correlation and covariance and all that sort of stuff, because the matrix math in there requires a particular orientation for that set of multiplies to work out. We're going to go ahead and let this particular random vector x be zero mean. So I'm going to let its mean values all be zero. You could certainly take care of the case when it wasn't, but I'm going to go ahead and let it be zero mean. Furthermore, I'm going to let the correlation, right? Well, because it's zero mean, the correlation is going to equal the covariance, because covariance is just a mean adjusted correlation. The means are zero, so those guys are going to be equal. I'm going to let it be the identity matrix. So one's on the main diagonal, zero's in the off diagonal. Because all the off diagonal elements are zero, we know x1 and x2 are uncorrelated. And just a reminder on this, uncorrelated does not guarantee independent, except in very rare cases like Gaussian. So we can only say it's uncorrelated. We can't say that this implies independence between x1 and x2. The main diagonal elements, what are those guys? That's the variance of x1 and the variance of x2. So both of these are unit variance, zero mean random variables. I don't know what the underlying distributions are. They might be something like some Gaussians. They might be things like exponentials. They might be a Rayleigh distribution. It could be all sorts of stuff, but we're just looking at the summary statistics. We're not terribly concerned at this point about what the underlying distribution is. Okay, so now we're going to run our x through a linear transform to create a new set of observations. Think about this. We had an x that was uncorrelated unit variance, zero mean, right? Maybe I have an application where I have a computer, right, that is good at generating things like uncorrelated unit variance, zero mean observations according to some distribution. That is often the case that we can do stuff like that. But maybe my application requires that I have something that's not zero mean and that isn't necessarily uncorrelated. Linear transformations can help us get there using these simpler or this other random vector x. So I'm going to go ahead and define my random variable y. It's just a linear transformation of x. And in this first case, so case 1 sitting out here, I'm going to let my transformation matrix A be a 0, 1, 1, 1, something like that. And I'm going to let my B be 1 and minus 1, something like that. So if I make this transformation on x, linear transformation on x, using this A and this B, what are the summary statistics? What are the basic statistics of y? Well, we can take a look at that. From what we had seen above, the mean of y, right, is just going to be the mean of x times a, but because the mean of x is all zeros, anything times 0, even linear algebra, is going to be 0, plus b, we're just going to get b. So we end up getting the mean of y as being 1 minus 1 in this case. Really easy. If I had started with 0 mean random vector x to get a desired mean random vector y, we just make our b in that linear transformation ax plus b, we make b equal to the thing that is the desired mean, right? So b in this case 1 minus 1 turns out to be the mean that I'm gonna get. What is the correlation, the autocorrelation of y? Well, again, we had some expressions up on top. We could go back up and take a quick look at that. We have autocorrelation here, right? We say an ARX A transpose. Then there's something involving a mu x and another thing involving mu x. Because our particular example has mu x both being 0, those two middle terms are going to disappear. And then we get out here BB transpose. So when I come back down here, I'm going to get, in this particular case, right, I get that ARX A transpose, where we have those two middle terms as being 0, and then I'm going to get a BB transpose, something along those lines. What was A? A was 0, 1, 1, 1, right? My Rx was actually just the identity matrix. So I'm going to write that as identity matrix, right? And then I'm going to get A transpose. Because A has this sort of off-diagonal symmetry, its transpose is equal to itself. So this one's a little bit weird. We see that A is equal to A transpose in this particular case. It doesn't have to be that way, but it is in this case. And then I'm going to add to it the outer product of B. What is the outer product of B? I'm going to have something like a 1 minus 1, and we're going to have it times a 1 minus, whoops, that's getting a little muddied. Let's go ahead and clean that up. A 1 minus 1 and close it out, something like that. So I'm going to get, what, 1 times 1 is the first element. That's 1. That's this term, right? And then I'm going to get 1 times minus 1. That's minus 1. That's that term. I'm going to get a minus 1 times 1. That's going to be this one, minus 1. And I'm going to get minus 1 times minus 1. That's 1. That's this term. So I get that guy. If I continue in this, then the identity matrix times anything is just the anything, right? So I don't have to worry about that. This guy doesn't really come into play at all. So I can do this by just taking AA transpose, something along those lines. If I think about doing that AA transpose, let's do the first thing. I'm going to take this first row and go across that first column, right? So 0 times 0 plus 1, 1 times 1, that gives me 1. Do the next one. I'm going to take that first row and I'm going to do the second column. So 0 times 1, 1 plus 1 times 1, that's just 1. And then I'm going to go down to the lower one. 1, 1, going on to the 0, 1. 1 times 0 plus 1 times 1, that's going to be 1. And then I'm going to have the 1, 1 and the 1, 1. So 1 times 1 plus 1 times 1 is going to be 2. So when I put this all together, and by the way, I think for many of you, it's okay. You should probably be able to do these basic matrix calculations. You should be able to do them. You should be confident and reminded enough about your linear algebra skills that you can do this by hand, especially since we'll have a final exam coming up, and it's likely you'll get to do a few of these type of calculations. But programs like MATLAB make it super easy too. So you should always be at least checking your work with MATLAB. And if you're getting a little stuck or the dimensionality is high, MATLAB would certainly be preferable to a hand calculation. So now I just need to add these two pieces up. This is element by element. That's how we add matrices. So 1 plus 1 is 2, right? 1 minus 1 is 0. 1 minus 1 is 0, and 2 plus 1 is 3. So the correlation, autocorrelation matrix of y is also a diagonal matrix. What does that tell me? It tells me that those derived random variables that make up my random vector y, those are y1 and y2, y has the same dimensionality as x, that they have zero correlation as well, right? So they are going to have a correlation coefficient equal to 0, something along those lines as well. If I look at the zero correlation, I shouldn't have said correlation coefficient. They have zero correlation. The little r is equal to 0. But the correlation, right, cy, is just acxa. Well, we had computed that before. That's what this guy essentially was, because in our particular case, rx is equal to cx. We had already done that calculation of arx a prime, which is equal to acx a prime, because r is equal to x. So in this particular case, we can just grab the result, right? That's this guy, 1, 1, 1, 2. Because the off-diagonal elements are non-zero, they are correlated. And I think I made a mistake when I said the other one. They have zero correlation. That's that kind of unfortunate terminology. We mentioned this before, right? Correlation equaling to 0, little r equaling to 0. But covariance equal to 0 is uncorrelated, right? Correlation equal to 0 is orthogonal. This covariance, these cross terms or these diagonal terms, that's the uncorrelated case, something along those lines. So in this particular case, they are correlated. We had started, right, with an uncorrelated set of random variables, and we were able to generate random variables that not only had a different mean and a different correlation matrix, but they became correlated, right? We're able to build a random vector y such that y1 and y2 have positive correlation, right, in this particular case. We might also note, if I just think about this again, y was equal to ax plus b. I'm going to go ahead and throw in what is a, what is b, and if I take a look at that vector style, y1, right, y1, this vector y here has y1 stacked on top of y2. y1 is equal to 0, 1 times x1, x2. And so I'm going to have 0 times x1 plus 1 times x2. That's just going to be this x2 part. And then I add in the 1 in there. So y1 equals x2 plus 1. And if I do the same thing for y2, I end up getting 1 times that vector x1, x2, right? So that's going to be x1 plus x2. That's this piece. And then I have a minus 1. That's this piece over there. So y equals x2 plus 1. y2 equals x1 plus x2. So think about that a little bit. x1 and x2 were uncorrelated. That's what we started with. y1 is just equal to x2, right? But it's offset. It's DC offset, if you will. It's offset by 1. No surprise that the mean, right? x2 and x1 were both 0 mean. x2 being 0 mean is fine, but if I add 1 to it, it becomes a mean of 1. What is that from? We come back here. That's this piece right here, right? The mean, the thing associated with y1, y1 has a mean of 1. We can easily see that from this expression. If I take the expected value of y1, it's the expected value of x2 plus 1. Expected x2 is just 0, so I get a 1 out of that. In the same sort of way, if I do the expected value of y2, that's going to be expected x1 plus expected x2 plus expected minus 1, which is just minus 1. That's going to be 0 plus 0 minus 1, so that's the minus 1. Go back up here, and we certainly see that. We see that verified as well. Furthermore, what do we see? If I wanted to know what is the variance of y1, it's going to be related to the variance of x2. Now, an offset of 1 doesn't change the variance, right? Because variance is a mean adjusted quantity. So the variance of y1 is going to be the variance of x2. We'd seen that kind of calculation before. What is that going to be about? That is this diagonal element, right? The main diagonal elements of our covariance matrix are the variances of our vector elements. So the first element on the diagonal is the variance of y1. And we can certainly see that the variance of y1 is going to be the same as the variance of x2, which was 1, right? If we went back up to the covariance matrix of x, right, x2 had a variance equal to 1. So we can certainly see where that first element of the covariance of y comes from. If you think about the variance of y2, right? Again, this DC offset doesn't matter because everything is mean adjusted. We're going to have the variance of x1 plus x2. Normally, we'd have to have the variance of the quantity x1 plus x2. Normally, you would do that out as variance x1 plus variance x2 plus the covariance between x1 and x2. But x1, x2 are uncorrelated, which means the covariance term, that cross term, is 0. So the variance of that whole right-hand side is just going to be variance x1 plus variance x2. That's going to be what my variance y2 is. And the variance of x1 is equal to the variance x2, both equal to 1. Add 1 and 1 together, you get 2. That's why we get this 2 down here, right? We can see it easily from just doing some basic operations on our original linear transformation expression. Okay. What else do we see in here? We see that y1 involves some x2, and y2 involves x2 as well, with some little bit of x1 added in as well. It is no surprise that there has to be some correlation between y1 and y2 because they both share that part x2. If x2 got really big, y2 is naturally going to get a little bit bigger because x2 is part of y2. That's this idea that we get these cross terms here that are non-zero. There is a correlation, and it's positive here because y1 depends on x2 and y2 depends on x2, right? So all of these elements in these vectors that we see are sensible. Just a little bit of supporting calculation down there. Variance of y1 is just the variance of x2, which is 1. Variance of y2 is the variance of x1 and x2. Each added together, that's 2. Let's look at one more case and then we'll be done with the lecture today. In this case, I'm going to look at a different vector b, same vector b, so b is still going to be 1 and minus 1, but I'm going to look at a different matrix A. So instead of having 0, 1, 1, 1, I'm going to have a 1, 1, 1, minus 1. You can do all the math yourself, or you can go to MATLAB. I'll let you do all of that. I'm going to just skip those. They're kind of boring calculations. Although you could have guessed what the mean vector is going to be for the same reason that it was b before, it's going to be b again. So again, we're going to create a vector y that is now no longer 0 mean. It is going to have means 1 and minus 1 reflectively, right? If I looked in the y1, y2 coordinate plane and I compared it to the x1, x2 plane, so if I had x1 and x2, we know that the means of both of those are going to come right there at the origin, right? If I looked at the y1 and the y2 plane, right? y1 has a mean 1, y2 has a mean minus 1, so it's going to get translated. That mean got translated over down into quadrant 4, if you will. Okay, so that one's straightforward. It's just like the last case. If I go through ry, though, I'm going to get 3 minus 1 minus 1, 3. And notice there's some symmetry on these off diagonals. That's going to be something that you'll see over and over and over again when we're talking real random variables, which is the primary focus in this class. And then if I go ahead and I compute out what is the covariance matrix of y, I get this guy. I get 2, 0, 0, 2. Think a little bit about this. Because the off-diagonal elements of the covariance matrix are 0, that tells me y1 and y2 are uncorrelated, right? What does that mean that they're uncorrelated? If I make y1 big, right, I don't really know whether y2 is going to get bigger or smaller. They are uncorrelated. There's no straight line relationship between them. It doesn't mean that they are independent, but it does mean that they lack that straight line kind of relationship. So in this case, even though I've got this kind of fancy A and I've got this B out here, just kind of like I did in the case one. Case one, if you remember, if I started out originally, right, I had uncorrelated variables x, right? The first case gave me correlated output y, and the second case gave me an uncorrelated output y. So just because one case gives you correlated doesn't mean that another case might not preserve that uncorrelated, origination or some element of the behavior or characteristics of x. You just got to go through the math. So here, y1 and y2 are uncorrelated, but we see one interesting thing, right? What previously x had each individual element with unit variance. This y now has double the variance in each. So the variability of y1 and y2 compared to x1 and x2 is twice, right? Variance of y1 equals variance y2 equals 2. Variance of x1 equals variance of x2 equals 1. So we doubled the variance in there, but maintained the uncorrelated, and we shifted the mean right off to that coordinate 1 minus 1. Next time, we will talk about the multivariate Gaussian. We're going to use a lot of these concepts that we've talked about. We're going to continue some heavy-duty linear algebra. We'll look at that next time.